Hi everyone, my name is Jake, and we're the Capybaras, and we made the C array programming language. So yeah, this is by Albert, Chelsea, Claudia, Faustina, Jake, and Mara, and we have this little camel with capybara on it because capybara is built on a camel. So yeah. Okay, so what is Capybara? So Capybara is a C-like programming language with statically sized arrays, and it's going to be useful for data manipulation and data science work. And yeah, so we have all sorts of built-in operations like matrix multiplication, transposing, slicing. Uh, we have element-wise addition, multiplication, subtraction, map reduce, and yeah, it's statically typed and scoped, and it has eager evaluation. So yeah, here's Capybara in one slide. We're just going to step through the code. As you can see, it looks pretty similar to C. We have like a normal C array, and then we have a matrix, but notably, the rows are delineated by a semicolon, including the last one. There's element-wise array scaling. We show that on the next line, where we multiply the array by 2, and then element-wise array addition, where we add the arrays together. And like I mentioned, you can also do this with subtraction, multiplication, and division. We also have slicing with 2D arrays, matrix multiplication. We just have to make sure that the shape of the matrices are work for the multiplication. And we have transposing the matrix. We also have the map function called here, which calls this +1 function, which just adds 1 to every element in A, and the sum and the reduce function, which sums all the elements in A into one integer. And we also do that on a matrix, and we sum every row into one integer. And then we also have like a length function, and we print out every element in the array. So yeah.
So on top of micro C, we've needed to implement a fair few bit of features to sort of flesh out our array programming language. Um, First of all, for simplicity and clarity's sake, we made it so that you can declare variables and initialize variables separately, and you can interleave the declarations throughout the page. Then we built on the special syntax for the different array types and array operations that involves semantic passes to make sure that the right types are being operated on. So you don't have like a 2 by 5 array with like a 5 by 1 array, or anything like that. And finally, we needed some way to modify arrays without introducing pointer semantics. So we uh, made it such that we could uh, pass and return arrays by value. So just to sort of take like that 1,000 mile view from the top perspective, we have the traditional 5 layer pass, um, like of a compiler. We tokenize it, we parse it into our abstract syntax tree. We semantically, we verify that there's like semantic consistency within the language, and then we translate it into LLVMIR. Uh, Notably, using the LLI LLVMIR editor allows us to link into the C standard library, which then means that we are able to access functionality that would otherwise be very, operating systems or hardware dependent.
So as Mara said, our Capybara language allows interleaved variable declarations and statements. We also allow declaration and initialization to happen in one statement. So you can either declare and then initialize, or you can initialize it to an expression on the right-hand side. For our array assignments, we perform a deep copy. So the initialization also performs a deep copy. As an example here, we are initializing this 3-int array called A to this array called 1, 2, 3. So on the right-hand side, this temporary array is essentially an array literal that gets allocated and created, and it holds 1, 2, 3 inside, and we will allocate a new array that will be associated with the variable name A and deep copy all the elements from the right-hand side array into it. And we might as well highlight some of our array operators. So these operate on either arrays or matrices, which are essentially just 2D arrays. And they include mathematical operators. Some of these are between arrays and arrays. Some are between arrays and scalars. But they include your basic addition, subtraction, multiplication, division, and also matrix multiplication. We also support access and slicing operators, the length of an array, transposing a matrix, map, and reduce. And these are all operators that are implemented in our code generation phase, and the results are stored in a newly allocated array, so the original arrays do not get changed.
For functions, we chose to have CAPybara allow users to pass arrays as an argument to these functions, and we specifically wanted pass by value semantics for arrays, which are similar to how structs are passed in C. So when the caller passes an array, the callee will allocate space on its stack and then deep copy each of the elements of the array to create the local copy that the function body can then use. One thing to note is that the data type and size of the array must be specified in the argument list when we're defining the function. So this does mean that you cannot pass or return arrays of an unspecified size. The reason we need this is because we must know type and size of arrays embedded in this type during compile time. This is definitely different than C, where all arrays decay to a pointer to their underlying type. So this is an example of how our pass by value semantics work under the hood for passing arrays. In this example, we have a 2x2 array of ints named A. So when we call print r2d where A is passed in, we first allocate the memory for parameter r on print r2d stack. We then are going to mem copy each element from A into R, and then R is able to be used throughout the body of print r2d.
Okay, so when we're returning array from the function, we retain the same pass by value semantics. So we also return arrays by value. In addition, we also require that the user specify the type and the size of the array at function definition time. In order to support returning array, we slightly modify the function signature of any function that returns an array, and we do this during the code generation phase. So there's two things that we do. Number one, we change the return type of the function to be void instead of the array. And number two, we add an extra argument to the argument list. So the type of this argument is a pointer to an array, and this array has the same type and size as the original return type of the function. For example, in the function ret array func1d, the original function returns an array to an integer, array to 3 integers. And so when we define this in CodeGen, it's a function that returns void and takes in an additional parameter, which is array1d return pointer. And this has a type of a pointer to the array of 3 integers. So to understand why we make these changes, let's run through an example program that uses this aforementioned function. So in the main function, when we reach the call to the function, the compiler first allocates a temporary array of 3 integers on the main stack frame. A pointer to the temporary array is then passed as a call to the function as one of its arguments. And then ret array func1d will then construct an array on its own stack as part of the return statement. The contents of this return array are then copied over into the temporary array, referenced using the pointer passed to the function. And then finally, as mentioned earlier in the variable declaration section, we then need to construct the array for the left-hand side of the statement, which will be the array that is referred to by array_x. And then finally, the contents of this temporary variable or temporary array are copied into the array_x variable.
Cool. And to end things off, we have a short code demo just to show you all what our language is capable of. So I'm going to switch my screen. Our language is similar to C and Java in the sense that everything begins in the main function, which we just defined to return void. And so as you know, our language is very useful for data manipulation. So Let's just imagine a use case. Let's say you've been going on a run for the past 3 days and you've recorded some data about your runs, such as how many miles you ran. So let's put that in an array, make up some numbers, as well as how many hours you ran on each day. So let's put that in another array. And you might be interested in doing some analysis of this data. So for example, you might want to calculate what your average mile pace has been over these 3 days. So typically mile pace is calculated in minutes, like how long it takes you to run a mile in minutes. But our data is currently in hours. And in a different language, if we wanted to convert from hours to minutes, we would probably have to write some sort of loop. But in our language, it's actually very easy to scale, element-wise scale an array. So if we wanted to convert this array from hours to minutes, all we would have to do is take our array and multiply it by 60. And to actually calculate our mile pace on each of the 3 days, we would want to divide the time in minutes by the distance in miles. And again, instead of having to write a loop to do that, our language supports dividing and multiplying arrays, as well as other element-wise operations too. So if we wanted to calculate our pace, we can just take our time in minutes array and divide it by our distance. So now we have our pace, and we might want to do some further analysis on each element of the array. For example, we might want to classify our pace as either being slow, normal, or fast. That is, we might want to have a function, let's just call it classify pace, that takes in our pace time. And if the pace is slower than some amount, say 10 minutes, then let's just call this a slow pace. It's between 7 and 10, just call it normal pace. And otherwise, that's a fast pace. And if we wanted to classify each of our times as instead of having a loop that applies this function to each element, CAPybara supports a map operator, which takes in an array that we want to apply the function, the map function to, and as well as the function to be applied. And map returns to us an array with the new elements after the function has been applied. So it would be an array of strings, and let's just call that classified. And then finally, we can print out the elements of this array just by writing a loop. And our language supports a print stir function, which will take in a string. And then we can try to compile and run this program. Cool, so everything worked, and it seems like our pace got faster over the course of the 3 days. So yeah, that's it for us, and thanks for watching.